Alrighty, everyone. We have just gotten our okay to start our final planetarium show of the day. So I'm going to put away our space trivia questions and change the vibe in the room just a little bit. And welcome everyone to the Morrison Planetarium. Really quickly, I just want to introduce myself. My name is Goose. I also like to go by Christian, but I'm going to be your planetarium presenter for the final show here in the planetarium today. And I'm really excited to have y'all here because you're my favorite place in this entire universe because everything that you see in purple is going to be one really big screen, thanks to the help of 6 different projectors all hidden throughout the room. And folks, I'm happy to have you here because you're in for a special treat. It's my favorite planetarium show to give. This one's called Tour of the Universe. And in this show, we're going to be starting off pretty close to the Earth, and we're going to be zooming all the way out to the very edge of the observable universe. So hopefully, by the end of the show, you won't have an existential crisis of where we are in space. So, just a forewarning: space is really big. And also, this show is completely live, so you're going to be hearing my voice as I free fly us through space. But before we begin, I got to go over some quick house rules just so that we're all on the same page and have a good time. First off, there's no food or drinks allowed in, so if you brought any snacks, make sure those are put away. We want to keep this place nice and clean, so thanks for helping us out. If you have any cell phones, smartwatches, anything that makes bright white light, now is a good time to put them away. These can be very distracting and takes away from the show, and trying to record on the big dome, it doesn't come out nice. Trust me, we have tried. So just sit back and relax and enjoy the show. Also, if you need to leave early for any reason, the exits are going to be at the very top of the planetarium, so always make your way up the stairs to exit. If the stairs are too steep to climb, don't worry, just remain seated. When the show's over, we'll have a staff member escort you to a lower exit when the show has ended. And also, folks, this show is quite immersive thanks to our 75-foot dome above us. If at any point during the show you start to feel overwhelmed, you experience motion sensitivity, all you have to do to ground yourself is close your eyes, take in a few big deep breaths. Then your brain will remember that you're sitting in a planetarium in San Francisco and not hurtling across the universe, at least not more than the usual. Hee hee hee. But with that being said, it looks like we're ready to go. So I invite you to sit back, relax, put those cell phones away, and let's begin our tour of the universe. All right, everybody. As I mentioned, we're going to be starting off pretty close to the Earth, but we're not right on the surface. We're just a little bit above it. We could see all the city lights down below. Ooh, it looks like someone has their flash on. But we're starting off at this really amazing man-made feature right in front of us called the International Space Station, or the ISS. Now, a lot of people tend to ask me, what is the International Space Station? People tend to hear about it in articles and news, but they don't really know what it is. Well, let me tell you, folks. The International Space Station is a research facility. It's a laboratory that orbits around our planet. And they conduct many different science experiments up here that's a little bit further from Earth and has less gravitational influence on it. If you have ever used Velcro, well, Velcro was invented on the International Space Station. So that's just some of the experiments that they've conducted up here. And what's really amazing is that this thing looks enormous here in our planetarium dome, but it's not that big in actuality. It's only about the size of an American football field. If you've never been to an American football game, that's okay. You can also use the entire museum that we're sitting in right now. That's about how big the ISS is. Fits about 6 to 10 astronauts at a given time, so there's quite a few humans living up here. Also, what's really incredible is how fast the ISS is traveling. It's traveling at a whopping 17,000 miles per hour, where it orbits once around the Earth every 90 minutes, and it experiences 16 sunrises and 16 sunsets a day. Whew, how romantic. Also, this looks really far away from our planet as well, but it's not too far either. It's only about 250 miles above the surface of our world. 250 miles, that's like going from San Francisco to Santa Barbara, a nice little road trip to get away with the family for the weekend, so not too bad. But to tell you the truth, folks, this is as far as we put humans into space nowadays, because traveling into space is quite costly. You got to build yourself a rocket ship, buy yourself one, or pay for a ride. And once you acquire that, you have to also acquire all the rocket fuel. You got to be able to escape Earth's gravity. And once you're out into orbit, you have to have a space station. You also have to bring all the food, water, all the air you're going to be breathing while you're up here. So the bill gets quite costly quite rapidly. But folks, the International Space Station is just the first stop in our tour of the universe. So now we're going to see it slowly fade away down to the city lights down below. And before we lose track of it, I want to add a nice little orbital path so you can see it as it slowly disappears. Alrighty, folks, we have left Earth and we're now looking down upon it. And from our perspective out here, we're now able to see the entirety of our planet. And I want to let you know that the space program that we're using here inside the Morrison Planetarium is something that you can go home and download if you want to fly through space just like how we're doing right now. The space program that I'm using is called OpenSpace. So if you go to openspaceproject.com, you can come across a link, you can download it, and it's a whole lot of fun. Now, just to let you know, OpenSpace is still being worked on. It's not finished yet, so we may come across a few bugs and glitches. If we do, I'll point them out. Hopefully, you can look past them. And also, OpenSpace uses a lot of processing power. It pulls information from satellites, so you can see some streaks across the Earth. These are real-time data taken from yesterday around noon, so that's the glare of the sun on the screen. So if you have an older computer, you may not want to download it, but if you got something new, give it a try. It's a whole lot of fun. But now that we're familiar with what we're using in the planetarium, let's make our way over to our nearest natural neighbor to us in space, the moon. And folks, we humans have been to the moon before. That was between 1969 and 1972, thanks to NASA's 6 Apollo space missions, which brought a total of 12 incredibly lucky guys to walk on the surface of the moon. They got to conduct science, and of course, they had some fun up here as well. They got to play some golf. But again, the last time we sent humans to the moon was 1972, a little more than 50 years ago or so. But don't worry, folks, we humans are making a return trip back to the moon in the next few years, thanks to NASA's new space mission in the works called Artemis. Pretty much with Artemis, NASA wants to send humans to Mars. But before we send humans to Mars, we got to figure out exactly how we're going to be able to live out here in space. So the moon is the perfect stepping stone to figuring out the logistics of doing that. What's also really incredible is that they're going to be sending the first woman to the moon, but not only that, they're also going to be sending the first person of color to the moon, but not only that, they're also going to be setting up lunar bases throughout our moon. Pretty much our technology has greatly improved in the last 50 years, so we're able to conduct much more science in a much more compactable size. And one place that we definitely want to set up a lunar base is the south pole of the moon. The reason why is because we found ice there. And that's going to be very helpful because we can melt that ice, pass electricity through it, separate the oxygen and the hydrogen, and both that stuff's really valuable when you're far away from home. So look out for any news about Artemis in the coming years. We humans should be heading back to the moon relatively soon. And folks, when you look up at the moon here from planet Earth, it feels incredibly close. It feels like you can reach out your arms and touch it. But the moon's really far away. It's about 240,000 miles away from Earth. Whew, 240,000 miles? That's a good distance away. Some of the adults in this room may have a car with that many miles on it. And if you take better care of your car than I do, you can even imagine driving to the moon. If you drove for 4 months, nonstop, going about 80 miles per hour, although I wouldn't recommend it, the roads out here are poorly maintained. Hee hee hee. And from here on out, folks, we're going to need to use a more useful measuring stick because at this scale, using miles, it's kind of like using inches to describe the distances between cities because space is so big. So astronomers use a more convenient measurement known as light speed. And light travels at a mind-boggling speed of 187,000 miles per second. That's about 300,000 kilometers per second. So while it took the astronauts more than 3 days to reach the moon, traveling faster and farther than any human has done so or since, it only takes light 1.5 seconds to cross that distance at the speed of light. That's kind of like a short pause in conversation. But at last, folks, it's time for us to leave the moon behind. So everyone say bye-bye, moon. So cute. And just like before, folks, we're going to see the moon start to slowly fade away into the vastness of space, just like how we saw with the ISS. And just like before, I want to add some nice trails so we can keep track of it, because again, space is incredibly large. So the lines that you're now seeing, one of them is the orbit of the moon, and all the other ones, these are the planet trails. And on our journey today, folks, we're going to be traveling much faster than the speed of light. We're going to be traveling at the speed of the human imagination, thanks to the help of computer models like OpenSpace, showing us the most accurate images and information available to us. And now the nearest star to us, the sun, should be coming into view. So here comes the sun. Do. And folks, the sun's also incredibly far away from us as well. It's about 93 million miles away from Earth. Whew. You thought the moon was far? The sun is incredibly far. And 93 million miles is a good distance away, but in terms of speed of light, it's not too far. For light to cross that distance, it takes light 8.5 minutes at the speed of light to cross that 93 million miles. Whew, not too bad. And this is a great concept to keep in mind, folks, because even though light is the fastest thing in the universe that we've come across, it still takes time to cross these vast distances. And again, this is a great concept to keep in mind, because let's say we're looking at a star 70 light years away from us. We're looking at that star as it looked like 70 years ago, because the light that just reached us took 70 years to get to us. So when you look at really far away objects in space, it's kind of looking back in time in a sense, which is really cool. But now that we have a nice bird's eye perspective of our solar system, let's do a quick refresher of what we have. Right in the middle of our solar system, we have our star, the sun. The closest planet to the sun, we have Mercury. Then we have Venus, Earth, we just left there, and then Mars. These are the rocky terrestrial planets. These are places where we can actually land a spacecraft on if we wanted to. And then past the orbit of Mars, we have the main asteroid belt. And this is where you can find a lot of space rocks, a lot of asteroids. And then past the asteroid belt, you have the really big planets, the gas giants, the Jovians. We have Jupiter, the largest of them all. Saturn, famous for its rings. Then we have the icy gas giants. We have Uranus, the funny one, and Neptune. And of course, we can add everyone's favorite and lovable dwarf planet, Pluto. So here comes the orbit of Pluto on screen on the very top left of our dome. And a lot of people don't realize that Pluto hangs out here in this outer part of our solar system called the Kuiper Belt. And I know a few of you in here are probably wondering to yourself, what's the Kuiper Belt? I've never heard of that before. Well, let me show you. This is the Kuiper Belt. So the Kuiper Belt is like a second asteroid belt past the orbit of Neptune. What you're mostly going to find out here are icy asteroids and short period comets that don't stray too far away from the sun. And what's really incredible is that we came across a lot of objects in the Kuiper Belt region in the year 2006. That's when our telescopes and technology greatly improved, so we're able to see much smaller objects much further away. And in that same year of 2006, we came across more than 400 objects out here in this region, and some of that stuff was bigger than Pluto. So we couldn't call all these things planets. There was just way too many of them. So all the astronomers across planet Earth had a great big meeting. They had to figure out what exactly you need to be considered a planet. And folks, that was the day in 2006 that Pluto went from being a planet to a dwarf planet. And I know a lot of people still have hard feelings about it. I still kind of do. But that's the really cool thing about science, because as our technology improves, we're able to make better observations and redefine things. So that's something I love about science, constantly updating and changing. But I'm going to put away the Kuiper Belt because honestly, that's just way too much to look at. And now, folks, I'm going to be adding on screen the many different spacecrafts we sent on the 1970s to explore our solar system. So coming onto screen, we now have the trajectories of Pioneer 10, Pioneer 11, Voyager 1, Voyager 2, and the latest of them all, New Horizons, which did a quick flyby of Pluto in 2015. We can see that interaction right over yonder. Now, all of these spacecrafts are all traveling fast enough to escape the sun's gravity and leave our solar system behind. But even the most distant of these robot adventures, Voyager 1, has not traveled as far as light travels in a single day. In order for sunlight to travel all the way out to the orbit of Pluto, it takes sunlight about 5 hours at the speed of light. 5 hours to get all the way out here. Not too shabby. But, folks, it's time for us to leave our planetary scale behind because now we're heading out into interstellar space, the space between the stars. Distance now becomes so immense, it's going to take us roughly about 4 years at the speed of light just to reach the next star system to us, the Alpha Centauri system. And it looks like Alpha Centauri is going to be the star system on our left-hand side. So we're right in the center of our screen. Alpha Centauri is on the left. Again, 4 years at the speed of light just to get the next star system to us, folks. But that doesn't put into perspective of how long it would take us if we traveled in a rocket ship. Well, if you got on a rocket ship today, made your way over to the next star system, it's going to take you roughly about 8,500 years. So I hope you bring enough snacks. But, folks, let's stop considering whether humanity has made its presence known beyond our solar system because now we're stepping inside something called the radiosphere. And again, we're now inside something called the radiosphere. This represents the current limits of the most distant radio signals humanity has ever broadcasted out into space. And it extends about 90 light years in all directions, emitting out from the Earth. This first began in the early 1930s with strong radio waves, early television, radar signal, and then later, the detonation of atomic weapons. All this stuff is emitting electromagnetic radiation strong enough to escape the Earth's ionosphere. And humans were broadcasting well before the early 1930s, but the earliest radio was not quite powerful enough to escape the Earth. Since all these signals are electromagnetic, they're traveling at the speed of light. So this is kind of like humanity's electromagnetic footprint in the universe. And of course, the radiosphere is constantly expanding at the rate of 1 light year per year. So is anybody out there listening? And folks, right now I'm going to be adding these many markers onto the screen. These markers indicate the many thousands of stars astronomers have discovered over the last 30 years. Each one of these markers has at least one or more planets orbiting around them. We call those planets exoplanets, and we're looking for any of them that are Earth-like with conditions suitable for life as we know it. So far today, we found more than 5,000 confirmed exoplanets in the nearby vicinity to us, 5,000 other worlds besides our own. And that number is going to be increasing as the years continue because we have space telescopes where their whole purpose is to find as many exoplanets as possible. Now, to say if any of them are Earth like with conditions suitable for life as we know it, well, we can't answer that question quite yet. Pretty much new space telescopes are being developed. They're being put on the drawing boards. They got to get constructed, launched into space. So we've got a little bit of a while before we can answer that one. But the more important point here is that quite a few of these planetary systems are within that 90 light year limit of our radiosphere, and they could have potentially received our signals. However, since radio waves travel at the speed of light, if there is anybody that's out there able to listen in, answer back, the communication delays between hellos could be decades in time. Now, to give you a quick example, let's say we live in a star system on the far left of our radiosphere. Let's say this one over here on the left. We find an alien civilization on the other side. We send them a text message. We say, hey, we're humans. It takes 60 years to get to them. They listen in, answer back, another 60 years to get their reply. Folks, that is a 120-year conversation in the making. And I can barely wait for a text message from my friend, so I don't know how that's going to work out. But of course, folks, planetary systems beyond the radiosphere, more than 90 light years away, have not heard from us. At least not yet, but eventually they will, as the radiosphere is always growing, but it becomes weaker as it does. But I want to put away the exoplanet markers, but I'm going to leave our radiosphere up on screen. Because as huge as humanity's electromagnetic footprint is, it is nothing compared to our Milky Way galaxy. So keep your eye on it. All right, folks, we're now looking down on our Milky Way galaxy. This is the galaxy we live in, and I have to ask, can anybody see their house from here? If you said yes, you have incredible eyesight. And folks, our Milky Way galaxy is incredibly large. If you wanted to cross it from one side to the other, it's going to take you about 130,000 years at the speed of light. It's enormous. And the Milky Way is so huge, we estimate that there's at least 300 billion stars in the galaxy. If our recent discovery of so many exoplanets just within our small neighborhood and this massive star city is any indication, there could be billions of planets and potentially millions of Earth like planets throughout our single galaxy. But before we leave the Milky Way, I want to show you what it looks like from the side. You're going to notice that we live in a big flat spiral disk. Kind of looks like a big pancake or a frisbee in space. And this is important because when astronomers want to learn about the universe, it's so much more easier for them to point their telescopes galactically north and galactically south, instead of looking through the plane of the Milky Way, which has planets, stars, gas, debris, things that block their view of the universe. So keep that in mind. We like to point our telescopes galactically north and south. That's going to come important in just a little bit. But folks, the Milky Way galaxy is only one of many hundreds of billions of galaxies that comprise the known universe. So in this giant leap, every single point of light that you're now going to see no longer represents a star, but rather the location of an individual galaxy. Each galaxy containing hundreds of billions, perhaps trillions of stars. And we live in a local galaxy group, which contains about 30 galaxies, large and small. Also includes the nearest large spiral to us, the Andromeda Galaxy, only 2 million light years away, just next door, and heading right for us. We're going to merge with it in about 5 billion years, so mark your calendars. And once that happens, the Milky Way and Andromeda will become one and will be Milkdromeda. It's the real name. Astronomers are bad at naming things. And as we continue expanding out, folks, you're going to notice that galaxies are not evenly distributed throughout space where they're in a nice little neat row, like ducklings. Instead, galaxies like to group together in large groups and clusters, or they create voids where there's very few galaxies or no galaxies at all. So we could see some nice galaxy clustering towards the center of our screen. We could see some voids on the very far left of the planetarium dome. And this picture that we're now looking at represents the closest 30,000 galaxies to us in a space over 300 million light years across. We got to give a special shout out to the astronomer by Dr. Brantoli, who compiled this amazing representation over decades of time with the help of other astronomers. And honestly, this is my favorite galactic map to fly through. So thank you, Dr. Brantoli. But now we have automated systems that are mapping even the most distant galaxies. So, folks, we're about to see the very large scale structure of the universe. And remember, every single point of light that you're seeing that's not a star, that's an individual galaxy. Whew, I feel small. And by the way, the large scale structure of the universe is not in the shape of a bow tie or a butterfly as we start to swing around. Remember when I mentioned that we live in a big flat spiral disk of the Milky Way? Well, if you line up the Milky Way galaxy, it would line up vertically, just like so. And again, we like to point our telescopes galactically north and galactically south instead of looking through the plane of the Milky Way. But we humans still want to make sure that there's galaxies through the plane of the Milky Way, so we have this purple survey right in the middle. You'll notice that we're still able to find galaxies, just not as many and not as far. Pretty much we have to wait for our technology to improve, and once that happens, we'll be able to map out all those areas that haven't been filled in yet, so it's just a matter of time. And speaking of time, we're almost out of it. So let's continue pressing on, because now we're going to be encountering these really distant, faraway objects known as the quasars. And the quasars are going to be represented by orange dots on either side of the large-scale structure of the universe. There they are. And folks, quasars are short for quasi-stellar radio sources. These blazing objects are all billions of light years away. So now we're looking so far back in the depth of time and space that the most distant quasars represent the universe at a much earlier age. We're nearing the very beginning of galaxy formation. In other words, with the quasars, we're viewing a sort of awkward, gawky teenage version of the universe. And before there was a teenager, there was a baby. So let's press back to a time before quasars, before planets, stars, and even galaxies began to form. Folks, we're about to see the very edge of the observable universe. And here we are at the very edge of the observable universe, folks. What we're looking at is something called the cosmic microwave background image, or the CMB image for short. All evidence indicates that the universe that we live in is about 13.8 billion years old. This is data compiled by Planck and other radio telescopes. And this picture is a very baby version of the universe, only 380,000 years after the Big Bang occurred, where space and time began. And this is not your typical photo either. This is kind of like a picture with a filter, if that makes it make sense. This is a temperature density image, where the light echoes of the Big Bang are color coded, with the lighter areas corresponding to the hottest, least dense regions, and the dark areas the coolest, densest regions. But these differences in temperature and density are extremely tiny. They vary no more than 1 part per 100,000. But these tiny differences eventually gave rise to that large-scale structure of the universe that we saw moments ago, that clumping and clustering of galaxies everywhere. Figuring out just how that happened is one of the larger challenges for cosmological research today. And folks, though our view here is of the outer edge of the known universe, the earliest light visible to us, that radiation actually persists all around us. It permeates the universe, stretching and cooling as the universe expands over billions of years of time. But folks, we only have one direction left to go, and that's going to be back towards planet Earth. So let's find a nice entry point through all these quasars and galaxies, and let's make our return trip back home. All right, everyone, we're crossing an expanse of over 13 billion light years. We present you with this view of our universe and the latest in cosmological and astronomical information. We're covering eons and observing objects billions of light years apart. We live in a golden age of astronomy with new generations of telescopes and spacecrafts that are extending the reaches of our eyes. And with that thought, everyone, I want to remind you that astronomy is for everyone. You don't need to be a scientist to enjoy the beauties and wonders of our universe. All you need is the night sky, and if you can, get away from the lights of our cities and look up. Even a good pair of binoculars makes for a decent first telescope. And there's astronomy clubs all around the world that invite people just like you to look through their telescopes and peer into the great beyond, allowing you to partake in the wonders that our universe has to offer. Now, astronomy as a hobby can offer an endless supply of satisfaction, and I do hope you'll join us, those who dream amongst the stars. But it looks like we just made our way back into the Milky Way galaxy. We're heading straight for that radiosphere. And of course, making our way back to our star system, our little neighborhood in the vastness of time and space. And folks, we're about to pass those spacecrafts we sent out in the 1970s to explore our solar system, passing the orbit of Pluto and the Kuiper Belt region. And we're making our way to the third rock from the sun, our homeworld, planet Earth. All the people that we know, love, ever learned about in history all live on this one planet. And now we're about to pass the orbit of the moon, the furthest we've ever sent humans out into outer space. And as we make our final approach back to planet Earth, folks, this is going to be the end of our tour of the universe show. And I want to thank y'all so much for stopping by and watching with us today. I hope you did enjoy it. But hey, look at that. We made it back home safe and sound just in time for dinner time. And that's all the time that we have for today. So thanks for stopping by, and I hope you have a great evening, everyone. Take care.